in the board. Thank you. Thank you, Tom, for starting that. And the president, Claude Haynes. The vice president position is open, but we appreciate Tom Mosden in helping us out to get speakers and to do other things. But we are still looking for vice president. So if you are interested, please send me an email. Our secretary is Gordon Rosner, and our treasurer is Alexandra Nachman. And then the board, Dave Kosho, John Kester, Bill Peters, Brooks Schofield, and Derek Youngson. And so if you do want to get in touch with us, please look at the bottom of our webpage under contact, and there are various email addresses there. Would like to just mention a few other folks. James Yoder, who's our property director. If you have anything that you want to have an astronomy equipment to donate to the club, we may have an auction once we return to in-person meetings. We have collected a little bit of stuff. Alexandra is also our events coordinator. And then Marty Pazanka is our webmaster and newsletter editor. Now, we're going to try something that could become a total disaster, but we have requests to assist with formatting your screen view to get the presentation to be as large as possible. So it varies depending upon your device. There should be a 3-dot icon up near the top right corner of your screen, or it will be just where you see the top of the kind of images of people's video. If you click full screen or enter full screen, depending upon your device, then that will make the presentation as large as it's going to be. And if you will click on those dots and choose the speaker instead of the panelist or a gallery. So if you click on the speaker, you should just see the video of the person who is speaking. And then near where, if yours on the side like mine is, near where the picture is, you will see the doubled arrows, and you can squeeze that to change the size of the image, the picture, the video, to be as small as it can possibly be. So I hope that makes sense. It's really hard to demonstrate the way that Zoom is set up because I can't show you what's on my screen because I'm sharing another presentation. So we're going to pause just for a minute for you to try and do that, and also to wait for the people to come back and reconnect after they've kicked themselves offline, which we know is what's really going to happen with that. But hopefully it'll make it easier for you to see the presentation.
So Claude, there might be one caveat. I've got it set to follow the host view, which my view is side-by-side speaker only.
Okay.
But I think what they could possibly control is sliding that the presentation bar that's next to the speaker and the presentation, slide it to the left and the speaker gets bigger, slide it to the right and the presentation gets bigger.
Right. Okay, great. Thank you. So I wanted to go through a little bit of the survey results. I really want to thank you for filling out the survey. We had about 80 responses. Most of you are members or you are considering joining. So if you are a no or considering, please contact Alex with your membership or renewal. And it's good to know how long you've been participating in EVAC. We did have a good mix. Most have been active with the club for 2 to 5 years, but we really have a healthy number of newer members and a strong group with over 10 years of experience. And what age range do you fall into? We're an older club. We're not going to kid ourselves. But we do have a promising number of youngsters who have also responded, and we're really grateful for that. When do you feel that EVAC should return to the live meetings? There is pent-up demand. The board is meeting each month. They felt it was a little early to return in April. We still have a lot of new infections here in Arizona, and there's a new variant from Europe that in a couple of weeks could produce a spike. the board is being cautious, and there were a number of comments about risk for older members. So we are aware of that. We've decided not to, we've decided that April will be another Zoom meeting. We're meeting in April again. Stay tuned for further announcements. When we return to personal meetings, we are planning on doing a live stream of the meetings. That technology does present some challenges, but we will try to present a quality experience as best we can in the library. Now, we encourage you to use the recorded meetings as a resource. A number of you have, and that's great. If you look on the website under events and meetings and select monthly meetings, the hyperlinks are there under the name of the presenter and their presentation. And this is an archive of all of our Zoom meetings during the pandemonium. So there is a good list of those now and a lot of great information. So I would encourage you to go out and if you missed a meeting or you're just curious, go out and check those presentations that have been recorded. This one is a little surprise. There was a strong response to the idea of EVAC offering more online offerings, and there was some really good input on class topics and learning requests from the members. So that was very helpful and very informative. And for more family-specific focus, there were no votes. Alex has experience at the now closed South Mountain Park site that Gordon also helped with. And we have some good comments and ideas on this question as well. So I think we may see a little more options for events or for outreach, rather other than just having people look through our telescopes, which could be kind of exciting. In terms of events, the board did authorize Alex to begin accepting requests for school star parties and public events. This is still on a case-by-case basis. Some schools don't seem to understand the concept of viewing after dark because we still get requests to say that they would like telescopes from 5 p.m. to 6:30 p.m. because it's a school night and people have to go home. But we will begin to see some more activity for events in the near future. And in terms of participation, a strong number of you have participated in many of the events and outreach. We also had a good number of people who submitted their emails to volunteer for the observatory or school outreach. We've contacted those new people, but some indicated a willingness to assist, but they didn't include their email. So if you are interested in volunteering at the observatory or for school star parties or other events, please send me an email to president@evaconline.org, and I'll pass replies on to Alex as well. And there are links at the bottom of each page of the EVAC website for contact if you need to get in touch with somebody. So finally, I would like to just say thank you for the survey results. We got a lot of good, thoughtful comments, and we talked about it at the board meeting earlier this week, and the board members have copies of those comments, and they were really helpful, and I really appreciate your participation in the survey. Things coming up, we have the Messier Marathon, Saturday, March 26th. It's at the antenna site. Check the SAC website or their Facebook for detail. So let me be a little specific here about location. It is at the Hovatter Road exit 53. It is not at the Salome Emergency Airfield site. So when you get on get off the freeway and you take that first road headed south, instead of turning left to go to the airfield, turn right and follow that road around the antennas. And there's a pretty easily marked turn where you would follow that down to the antenna site. Give your respects to Steve Coe here. And this is the location. The antennas would be over here. There is some extra parking here. Check the website from SAC. If you have an RV, they're suggesting you point north-south so you can kind of get more people into the area. And there will be some updates on their website, or for Facebook, you can look up All Arizona Messier Marathon, and I think Tom or others will post information there as well. And if Tom, I know, is online, but I don't think he has a microphone on his computer, but we'll relay any information, or if you have a question, and I think he can see those in the chat or the Q&A, and then he would be able to respond as well. A couple of other things: Marston Exploration Theater at ASU. They have Wednesday, March 23, 7 p.m. via Zoom, a live presentation on the night sky. Rick Alling does these. In addition to some things you see from the planetarium program, but they usually have a guest speaker. They may have some students who have done some research. It's kind of an interesting program. You do have to register, but it is free. And they do these every 2 weeks or so, I think, through the school year. And if you enjoy those kind of programs, you may find that to be a fun activity. Just check under, look up Marston Theater and at ASU events, and you should be able to find a link. Also coming up is Origins Project Foundation. This is April 10th, and this is at the Orpheum Theater downtown. Richard Dawkins and Lawrence Krauss will be having a discussion, and then a screening of the film called The Unbelievers. April 11th, there is a panel discussion with Barry Barish, who is a Nobel laureate, Michael Turner from the University of Chicago, Lawrence Krauss, and Neil deGrasse Tyson, some kid you may have heard of. This is a ticketed event, and they're not cheap. EVAC, we're not sponsoring this in any way. I'm just giving this as an announcement for you, but we don't get a cut of anything that's there, but just to give you some information on it. And that's it for all of the things I have. So Tom, I'm going to turn it over to you to introduce our speaker, Phil Mauskopf.
All right, thank you, Claude. It's my pleasure to introduce Professor Phil Mauskopf. I'm going to give the long version of the introduction. Phil received his PhD degree from the University of California, Berkeley, and since 2000, he's been a professor of experimental astrophysics with Cardiff University at Cardiff in the UK, where he helped start a world-leading group in the area of astronomical instrumentation for terahertz frequencies. He's currently a professor with Arizona State University here in Tempe. His research areas include experimental cosmology, in particular designing and building new types of instruments for measuring signals from the most distant objects in the universe, along with solid-state physics, atmospheric science, quantum communications, and cryptography. So that's a pretty broad swath there. And you have a pretty broad group of graduate students to complement that. He particularly enjoys the opportunity to pursue interdisciplinary projects within the ASU community, as well as collaborating with researchers at other universities and research institutions, such as Caltech, JPL, University of Pennsylvania, Columbia University, NIST Boulder, Cardiff, and the Neil Institute and IRAM Observatory in France. His research includes development of new types of quantum-limited photon detectors, optical elements, and readout electronics, and has applications in solid-state physics, atmospheric science, and quantum communication and cryptography. And Professor Mauskopf has developed detectors and optics that have been deployed on space-based, balloon-borne, and ground-based telescopes. And most recently, he's one of the leaders of the Management and Advisory Committee of the Starshot Breakthrough Program, which requires unconventional techniques to accomplish its goals. So please welcome Phil.
All right, well, thank you, Tom. Thanks, Claude, and thanks everyone for coming. I'm gonna share my screen. I think, let's see, if this works. So yeah, as Tom said, I'm interested in a lot of different things. So tonight I'm going to talk about one of the more literally far out projects and applications of the work that I do, which is in figuring out or understanding how we might be able to reach the nearest stars, both and then know that we've reached them, so navigate and then also communicate. So you heard the introduction. A few, just before I start, a couple of possible, if you want to hear more or read more about some of the stuff I'll be talking about tonight, we have a web page set up that was set up by people at ASU and the Interplanetary Initiative that has information on the ASU Starshot work that's going on the communications research. Also, if you want to hear me talking more on the radio, there's a podcast where I talk about some of the other topics that I won't be able to talk about tonight, including superconducting detectors, kinetic inductance detectors, instruments like balloon-borne far infrared instruments, ground-based. BLAST is a balloon-borne one. TOLTIC is a ground-based instrument. SphereX is a satellite that is scheduled to launch in a little over a year and a half. So, and then also before I start, and I can see there's chat. So, oh, there, Tom's put those in there. Also, before I start, because I'm going to be talking about the projects that are funded by the Breakthrough Foundation, I do want to comment, I know Tom was asking me about this, that the Breakthrough Foundation, like a number of other foundations that fund research, scientific research, is funded by a dot-com, basically a tech billionaire named Yuri Milner, who was born in Russia. He is not a supporter of Vladimir Putin, and his own company and holdings have been independent of Russian funding for over a decade. But I'm just putting here, there were two statements that have been released since the invasion of Ukraine by Russia, and I know that we all have links in our lab. We have links. We have current students, former students who have family from the Ukraine. My wife and I both, half our family originally comes from Western Ukraine. So this is a sensitive topic, but I just wanted to put these up here. So the Breakthrough Prize Foundation and the Breakthrough Initiatives Organization, both of these from the Breakthrough Foundation, have both come out with statements, and actually the head of the foundation is somebody named Pete Worden. Pete is a former U.S. Air Force general. He was in charge of the Star Wars initiative under Ronald Reagan, and so he's the head of the foundation. And so you know, he and Yuri Milner and the rest of the foundation have released this statement first on March 3rd, and then a second statement, and both of these were accompanied by the foundation donating money, I think up to now $6 million so far to the efforts to, here's a $3 million donation for victims of the conflict. And then there's another one. This is a second statement and a second donation to supporting more victims of the conflict. And there's links to the open letters and things like that. So anyway, I just wanted to get that out of the way. We are, you know, doing our work and, you know, exploring the universe and continuing to do all of this, but obviously there's context in our lives. We've had coronavirus, now we have you know, other conflicts. So okay, so what I will talk about, or the context of what I will talk about. So I'll talk about how to navigate to the stars, and how, if once we are able to navigate to the stars, how we can communicate and send data back. And what the context for this, or one context, is this proposed project that was proposed by and originally announced by Stephen Hawking, who was on one of the people, head of the people on the panel before he passed away, called Breakthrough Starshot, which is a proposal to launch the first human-built interstellar probes, the first probes to reach other star systems. And the goal for the project was to launch these probes within sort of the middle of, or around the middle of the 22nd century, 21st century, so not quite 22nd. So launch in the mid-century, in around 2050, and launch and reach speeds that are sufficient to have the probes arrive within a reasonable or a human lifetime, and send back data, because that's the point of exploration, is to learn and explore the universe. And in order to do this, the proposal was to target the Alpha Centauri system, which now we know there's, around Proxima Centauri, there are at least 2, more likely 3 planets, 2 of which are, I think, very close to the habitable zone. And in order to reach this velocity, you need to have a very, very lightweight payload in order to be able to accelerate it to that speed. And so these are some images that have been created through this project. The project started about 6 years ago. And in the beginning, there were a lot of different approaches. So the main issue and the main questions that were being asked were, how do you do the propulsion? I'm not going to talk a lot about that, but there were a lot of different options that were considered. And there are a lot of fun people working on it, that I've started to meet people who work on some of these more out there ideas. But basically, what was settled on as the baseline was an idea to use laser propulsion. So a high-powered laser. Originally, one of the ideas was to put the laser on the surface of the moon in order to avoid any atmospheric losses, but that was considered to be a little bit too ambitious in that we've never actually built anything on the moon yet. And so the baseline currently is to build the laser on the surface of the Earth. It would be a very large area laser that would consist of millions of small individual lasers, all phase coherent and combined together so that they would pass through the atmosphere fairly dilutely, and then combine all focusing on the light sail, which is shown here, depicted in artist's impression, which would be a few meters by a few meters with the tiny chip satellite in the middle. And so the Starshot project has grown, and there's a large and growing number of people that are on the advisory committee, and there are also now even more people working on the research and development in the different areas. So as I said, the objectives are to send the spacecraft to a star ideally with a planet in the habitable zone, which we know already there are some within 5 parsecs, and to record some science data of the star system, ideally related to the planets around the stars, and send that data back to Earth within 30 years. And one of the keys is the goal is to do this sort of at the cost level that is on the scale of less than, significantly less than, say, JWST in current dollars. So the the project identified 3 main challenge areas to do this. The first one is building this giant laser. This is called the photon engine because it's the engine that drives the Starship. And so the question is, how can we? Is it even possible, feasible to build something where we have lasers somewhere on the surface of the Earth or the Moon or in space or wherever, but that are capable of being coherently combined on the sail in order to accelerate it for long, and be focused long enough to accelerate it to the 20% the speed of light. And if you calculate what this means in terms of a power, it's on order of a few hundred gigawatts of power over 10 minutes or so in order to achieve this speed. And by the time you're at 0.2c and you've been 10 minutes at this acceleration, you are already past the orbit of Mars. So it's pretty fast. So then one obvious next question is, so this acceleration is a very large acceleration and the laser is a lot of power. Is it even possible to develop a material that would be reflective and be useful as a light sail, but that would be lightweight and reflective enough and not absorb any of this light and heat up and burn up, but also under the acceleration and this beam that you're pushing it with, mechanically be rigid and stable enough. And actually one of the important things is to not like veer off and just accelerate out of the laser beam. So there's been a lot of work done on self-aligning materials, et cetera. And so this was also considered a large challenge and an area of research. And I'm not going to talk more about these 2 areas because I already think I have like over an hour of stuff to talk about. But there has been a lot of work on both of these 2 areas. The photon engine work is led by Wes Green, who is in Colorado, and it has involved a number of groups all around the world. They're basically finished with their phase 1 R&D, and their conclusion is that yes, they have actually developed, one of the important things is they've developed a simulation and code which should enable them to build this and coherently combine this large array of lasers. Again, how the details of that, we can maybe discuss in questions later, but I'm not going to go into now. The sail material is being led by Harry Outwater, Caltech. He has a group of another group of people from all around the world that have been working on this. Both of these efforts have been funded at the level of $2 million for a phase A R&D. And then the third area is the communications, which is, okay, if the photon engine works and the sail works and we can accelerate this thing, what do we put on the chip or on the sail, how to integrate into the sail in order to send data back from that distance? And then is that even possible? So how do we receive useful data over interstellar distances? And then I put down here a 4th area, which is not one of the first 3 priorities, but there's other things: navigation, data recording, power. How do we design this chip, this tiny low mass spacecraft to be able to make a flyby at 0.2c of a planet around a star system and actually get near enough to it, so navigate near to it, and then be able to record the data in the first place to send back. So there's lots of, so I guess what I would say is one of the things that people who know me, who maybe I work with in the lab, they know that I really like working on projects where most people's reaction are, oh, that's totally impossible. There's no way you could possibly do that. So this project is as close to that as I've ever come. So I'm going to talk about 2 areas because first I'm going to talk about navigation because I think this is it's an interesting topic. but most of the time after this, I'll talk about the communications problem. So, so the questions for navigation is a difficult problem if you're traveling between the stars. So, I mean, a couple of fundamental questions is how would you do it? How do you build, how do you navigate when you're in interstellar space? Currently, I guess, and I'll talk about this more, deep space probes, you know, have different ways of navigating, but one of the ways that they do it is with the communications back and forth, ranging between the Earth ground stations. Obviously, that's not going to be possible if you're in interstellar space. And I guess the second, more maybe other fundamental question is, how do we navigate these tiny probes to be able to pass by the stars and even better, you know, planets? How do we hit a target that is so small, so far away? And then for the communication side, which is what I'll talk about next, how do we communicate with probes or spacecraft that are at interstellar distances? And what are the mass and power requirements on board, and what do we need to build on the ground in order to receive the signals? This is the ultimate sort of deep space network. And then is it possible, given, you know, practical questions and fundamental questions, to receive images from these probes? Okay, so moving through to deep space navigation, as I said, the current technologies that are used on spacecraft for deep space navigation are a combination of star trackers, clocks on board, Doppler or lighthouse. So velocity measurements is another way of doing this. So you can use radio sources. So in principle, if you have, so these are not what are used. So star trackers and clocks and range finding are the three main things that are currently used, but these are other ideas for things that you could use. So you could use Doppler or lighthouse velocity measurements. And then the other one, which is used, is range finding. So 1 or 2 way light travel times, for example, or, you know, looking at sizes and separations of objects. So the real question is, you know, for all of this, what is your position? So where am I with respect to my origin, right? Where you started. And you really want to know, you know, not only where you are, but which way am I going and how fast? So what is your velocity? So you want to locate yourself in 3-dimensional space and in 3 dimensions of velocity. If you're doing this, you know, in your car, you use, or if you're on a hike somewhere, you use a GPS system. And this is a system of trilateral range finding. There's satellites that are all sending signals down, they're received, and each one of the satellites is equipped with a very accurate clock. And so by using the differences in the times from these characteristic signals that they send, you can get X, Y, and Z position and velocity. And you can do this, we do this all the time now. So this is very well known. So I guess people have started thinking about, you know, how you might do this beyond the Earth. And so there's talk now both for cislunar missions and then Mars and beyond of doing some sort of system which would allow autonomous navigation throughout the solar system, so that you wouldn't have to necessarily rely on ground-based, Earth-based deep space networks. So currently, radio Doppler and range finding with the deep space network is one of the ways that we use for deep space navigation. Also, what's used is so you have a star tracker on board, an imaging system that tells you what is your orientation. And then you can also do near object navigation with imaging of, you know, so planets, for example, or your destination target. And you can have onboard autonomous software. And this is now becoming more and more common in exploration around in our own solar system. And so there's been recognized that there's a need for more standardization and automation for future travel throughout the solar system. there's various studies going on. This is just an example of one from Caltech JPL. This is called a Deep Space Positioning System, the DPS. So this would be basically an instrument that you would bolt on to every deep space solar system probe that would have all of the sensors and then processing required to orient yourself in the solar system. And it has a variety of different tools. You can see some of them here: a narrow angle camera, there's a motor that allows you to scan the camera. There's a periscope here. There's a wide field, I think a star camera, and there's mostly this is cameras and ways of orienting yourself. There are a couple of other important things. So there's the star tracker. There's a radio, software-defined radio inside. There's this camera, and one of the key things is this deep space atomic clock. So this thing is part of the integrated instrument, and it provides very accurate time stamping, and this allows autonomous navigation, which is independent of, say, ground-based, time referencing. So I've circled that because they launched one of these things in 2019. So another development is this deep space atomic clock. The goal is to improve the timing stability and timing resolution of onboard space clocks. And so this system is about approximately 2 orders of magnitude, I think, better than what is currently flying on the generation of GPS satellites that we have. 50 times. Good. I was right on my order of magnitude. By the way, if I'm within a factor of 2, I always say that's pretty good. It's not tiny, so it weighs almost 20 kilograms, and it uses about 40 watts. So if we want to make this in a 1 gram spacecraft, then we've got a long way to go. All right, but because of these new technologies for clocks and new technologies for these star cameras and integrated systems, people have been thinking about flying satellites that are like the GPS, but spaced throughout the solar system to provide beacon-like signals that could be used to have even more compact, smaller orientation systems, just like you have in your phone on your spacecraft. So this is an idea that people are working on. This is like the GPS, the Earth orbiting beacons, which are these GPS satellites in medium Earth orbit around 20,000 kilometers, so not quite at GEO. And these have these radio transmitters and onboard atomic clocks. And they're precision's limited by the onboard clocks and atmospheric drag and also gravity fluctuations. So you could do this in the solar system with beacons that are spread out throughout the ecliptic plane. Since mostly we only want to travel, we usually keep traveling throughout the ecliptic plane in order to go from planet to planet. And I'm going to move quickly on to through this because there's some calculations here for the signal to noise and how you would do this. But the most important point is that you could also, and one other point is you could also do this with natural clocks. So there are natural clocks spread throughout the galaxy. These are spinning neutron stars that have beamed emission, which sweeps around and passes through the solar system and through the Earth periodically. These are known as pulsars. They're very stable because they're just the orbital period of the spinning neutron star. And they're at a known sky location, so you get a position reference, you can get timing, you can use them for navigation. The problem is that then the signal strength, there's not that many of them. The signal strength is relatively weak. So in order to detect these and use them, you actually need a fairly large antenna on board. But another comment is that either artificial GPS satellites have been used for this too. So artificial pulsed signals spread throughout somewhere around the Earth or throughout the solar system, or natural ones like pulsars can also, if their timing is good enough, can be used to measure stability and measure large scale gravitational waves. And people are currently doing this. So this is another interesting science topic, which most of what I do is related to trying to measure things like primordial gravitational waves or other signals from the early universe. And because of that, one of the things that we can use to measure signals from the early universe is measuring the cosmic microwave background. And so because of that, I also wanted to comment that for Starshot, if you are traveling in interstellar space, and you are traveling at some speed that is 20% the speed of light, then you can actually use, if you want to know what your velocity is in the galaxy or with respect to the rest frame of the universe, in fact, you can use the cosmic microwave background, because the cosmic microwave background is actually a very bright, by far the brightest source of photons in deep space, in interstellar space, at millimeter wavelength, so at a wavelength of 1 millimeter, and it will be redshifted in the direction that you are traveling away from, and it will be blue shifted in the direction you're traveling towards, and so it will actually be redshifted by quite a lot if you're traveling at 20% the speed of light. And so you don't need necessarily a very large antenna. These are millimeter waves. You need antennas that are millimeters or maybe slightly larger in size. And you don't even need that sensitive a receiver to detect it, because the signal is fairly large. Plus you have a lot of time, because it's taking 20 years still to go from one star to another. So along the way, you could say take a week and then figure out your direction just by measuring the CMB. And this has been thought of by other people. So Mason Peck, who is a professor at Cornell, who was previously was the NASA's chief technologist, has been working on a slightly different idea, but related idea, which is to use the relativistic distortion of stars in order to measure your velocity vector. And so the way that this works is that if you are going at relativistic speeds, then a scene in front of you, the direction you're traveling, seems to shrink in size, and the scene behind you seems to expand in size. This is just due to the path, the way that light travels at a constant speed, independent of direction, and so, or independent of your own speed with respect to the scene that you're looking at. And so if you're traveling at 20% the speed of light, then this would be a measurable distortion, and you could just take a star camera and then know where the position of the stars should be relative to each other, and then measure their relative offsets or shifts in positions, and you could then use that to tell which direction you're going. All right, so so that's the navigation part. So there's a lot of ideas about navigation and how you would do it. I guess what I didn't mention about navigation is, even if you could measure where you are, if you know where you are and you know what your velocity is, you still need to do something about it if you want to be able to, go somewhere, change your trajectory. And I haven't talked about that because, that's a hard problem. I mean, there's people starting to think about it for these very small spacecrafts, but basically you need some power source in order to be able to move. And there's some ideas. There's using the interstellar medium is one idea, or even using the laser that we're using for acceleration, even though it becomes dilute by the time you're very far away, but it's still probably strong enough to be able to maybe change your trajectory somewhat. But anyway, there's lots more that could be discussed about that problem, but I'm going to move to the communications one because that's the one that I'm mostly working on. So on the communication side, the questions I mentioned at the beginning, can we send and receive images from these tiny flyby probes? So the proposal is to send these, well, we already talked about this. So many unsolved problems, so power source, navigation, course correction, acquiring images and sending back data. So the goal is to receive images that are, on order of 100 kilobytes in size. And I'll show some examples of images that are, different sizes. For deep space communications, the current technology that we use for deep space probes are radio communications. The next generation, though, of communications, deep space communications, is optical, and basically going up in frequency gets you a number of advantages. And so there is going to be the first. So there have been some demonstrations of optical communications between the Earth and the Moon. There's going to be the first deep space past the Moon optical communication system will be flown this year, fingers crossed, on the NASA Psyche mission, which is led by Lindy Elkins-Tanton at ASU. The ground station, so that's going to go to 3AU. Psyche is an asteroid in the main belt, and it's going to be sending data back as it's traveling using an onboard laser. And the ground station is going to be using the Palomar 200-inch telescope with a superconducting nanowire single photon detector array. In order to scale this from the Psyche DSOC, as we'll see, to something that could be useful for a Starshot type mission, we need onboard much lower mass and lower power transmit systems, and we need probably much larger area ground-based receive systems. So here's an example or a summary of sort of the current technology and then what we need. So a communications example for deep space of a recent mission, a good example is New Horizons, which is the mission that is now currently flying out through the Kuiper Belt. It did a flyby of Pluto and made some very interesting and beautiful images of Pluto and Charon and the system. It does, so its navigation is by two-way Doppler distance and velocity measurements. Plus, it has onboard accelerometers, which have integrated velocity accuracy total of a few millimeters per second, which is pretty good. Plus onboard star cameras with arc-second resolution. And so that's the navigation side, which I'll say maybe one more thing about, because we had a great talk from this company, local company you probably know, maybe some of you have worked there. I would fully believe that, but that was responsible for the navigation solution and steering New Horizons to hit a very small target at Pluto. The downlink system is an onboard 12-watt X-band radio transmitter. This is a picture of the satellite. This is the 2.1 meter Cassegrain antenna. Obviously, this is not 1 gram, but it was able to, and the ground station it used to collect the data was the Deep Space Network 70-meter dish over a period of a year at a data rate of about 1 kilobit per second. So here is what you get with New Horizons at that data rate. You get an image like this of the moon Charon. This is taken from 15,000 kilometer distance. The speed that it's flying by is not that fast, 0.00004 times the speed of light. Distance from the Earth, again, not that far, 0.0005 light years. So we're trying to ramp up from this to Starshot by several orders of magnitude. And the downlink rate was approximately 1 kilobit per second, and it took about a year to downlink this data. So what are we trying to do with Starshot? Well, we'd like to fly through a star system, get, closer than, if possible, probably ideally much closer than 1 astronomical unit from any planets in the system. One of the ideas with Starshot, of course, is that you're not just, once you build this giant laser, you're not just going to launch one of these, you can launch many of them. So there is a sort of random factor where you can say, okay, we're going to do a scatter shot. So not every single one has to be successful in terms of the flyby. But it's a lot farther away. So 4 light years instead of 4 thousandths of a light year. The downlink rate that we want, though, in order to get images back and get 100 kilobytes of data in a roughly a year, is between 1 and 10 bits per second, or maybe even 0.1 bits per second if you calculate that over a year. And so the thing is that the link budget is really difficult because it's very far away. It's 4 orders of magnitude in distance, so 8 orders of magnitude in signal spread. This, by the way, is an example of a 1 kilobyte or even less, but approximately 1 kilobyte image of the Earth. So this is an image of the Earth that's been downsampled or reduced to 1 kilobyte of data. And you can clearly see a lot of stuff in 1 kilobyte if you can focus on the Earth or on a planet like that. So anyway, just comparing the parameters between New Horizons and Starshot, this is just the communication system on New Horizons was approximately 30 kilograms, transmit power 10 watts, aperture 2 meters, about 6 gigabytes of data over a year. Starshot, we're looking at, ideally about 100 kilobytes, so a lot less data, but also a lot less weight and a lot less power, a lot less power and weight. We could possibly, if we can design something, use the sail if it survives the trip of about a meter in diameter. But anyway, so what we can do is we can calculate, all right, how many orders of magnitude, this is one of the first things we wanted to find out, how many orders of magnitude away are we from New Horizons to what we need for Starshot? And if you create a figure of merit, which is just, what is the requirement on how many kilobits per second you need times the distance squared divided by some parameter, either the weight in kilograms or the power in watts, both what is the available power on board. So in either case, we're off by about 8 or 9 orders of magnitude from New Horizons. And that's a lot. So what can we do about that? Well, New Horizons is not, as I said, necessarily the best example, because maybe we should already be considering optical comms as sort of the current technology. It's not flown yet in deep space, but it's already been integrated and tested on Psyche. So this is the Deep Space Optical Communications demo that will fly on the Psyche mission, and the ground station, I said, is Palomar. There's an uplink system, which is a 1 meter telescope with a 5 kilowatt laser. And the onboard system, you can see a drawing of it here. It's a laser emitting with a collimating telescope that focuses the beam. The diameter of this is 22 centimeters. It's a 4-watt laser. And the total mass is about the same as the New Horizons communication system, and the power is a little bit higher than but the transmit power is about the same, so the total power is about the same as New Horizons. So how does this compare? So here's the uplink, here's the downlink, here's an example of the detectors. So if you look at the data rate, so actually I forgot to correct this one. So there's a paper where they give the data rate as maximum data rate is about 1 megabit per second. But if you actually look more recently, and what they've calculated is the data rate should be more like 250 megabits per second. Okay, there's a question which I will answer in a second. So the data rate that we expect to be able to get from this system from Psyche at 3AU is 256 megabits per second, which I always say to me is amazing, because the data rate that I get that is going out through my computer into Zoom in my house through whatever cable or optical fiber I'm getting is actually much lower than that, and often quite a bit, several orders of magnitude lower than that. And this is coming to us from 3AU away. So that's pretty good. And it's actually, many orders of magnitude better than New Horizons. Approximately 3 orders of magnitude better, and I haven't corrected this one. So basically, though, to be conservative, we still need 4 to 8 orders of magnitude increase in our communications figure of merit over the DSOC. So, let me address the question of the background. So there's 2 potential answers to the question of the background. So the first one is that the probe is traveling through the star system, but the whole star system, Proxima or Alpha, but Proxima, we're going to go to Proxima, which is fainter, but it's moving with respect to it transversely with respect to on the sky at approximately 25 kilometers per second. So the probe, as it goes through, will rapidly, after it's through, will rapidly move away from the star. So it takes only a week or two for the probe to be able to be easily resolved from the away from the star. And the other answer to the question too is that one of the things that we need, one of the technologies is, so the signal that we're looking at will be a laser transmitter with a very narrow bandwidth in the infrared. And so one of the technologies that we obviously would like to have is very narrow band filter in order to remove as much background light as possible. So at the right filter band. One of the challenges, of course, is that the probes, may be moving at slightly different speeds. So we can't just have a fixed filter. We have to be able to find the right wavelength and find, exactly based on the speed of the spacecraft. So those are 2 possible answers. There's a lot of really good questions because this is, just a really hard problem. So, anyway, I may not be able to answer all of the questions. That's part of the reason why it's fun, because we're still working on it. But so the question is, how do we get these 4 to 8 orders of magnitude? And so you can use these different parameters to figure out what is the signal to noise, or what is the data rate we can get from a given, basically this is a link budget type calculation. It involves, the diameter of the light sail, assuming that we can focus diffraction limited, the area of the collecting area on the ground, so the area of our deep space optical network collectors. It also is related to the frequency, and as I mentioned, the bandwidth of the light that we're looking at, how much power is being emitted, what's the transmit power, and then another thing is in the encoding, how many bits can we encode per photon or per pulse that we're detecting. And when you put all these things in, I like to do it this way, even though for a laser it's not really accurate, but to talk about the number of photons per second per hertz per mode, if we have a single mode fiber, say, connected to our ground station, each one of our ground station elements. So how many photons per second per hertz per mode do we get? And we want that number to be greater than 1, or on order of 1, if we're going to have 1 for each bit that we're detecting. So you can calculate this for Psyche, for the DSOC. That's there are lots of so the filter technology is actually one of the key areas that we're interested in. I'm commenting on the chat just so you know. But for Psyche, we can calculate this rate, and we can see that this should work for Psyche at 250 megahertz. So this equation gives us a number that is reasonable for Psyche. So we can use this equation, and we can just scale these different things. And so the question is, how do we get 4 to 8 orders of magnitude? And this is now scaling on the figure of merit with respect to the transmit power. Okay, and so the question is, how do we do this? So here's a table just showing rough orders of magnitude that are potentially we could gain over what is currently being planned for Psyche. So potentially if we optimize the encoding and do something really clever, we might be able to gain 1 order of magnitude, say, over Psyche. So instead of 1 bit per photon, which I think is the baseline assumption, we might get 10 bits per photon. And if you're interested in how you do that, then that's a long discussion. But maybe the easiest way to gain signal is to increase the diameter of, or the size of our collecting receiving area on the ground or wherever it is. And so here I've said, well, going from say 10 square meters, which is the area of the Palomar 200-inch telescope, to building a dedicated square kilometer of optical receiving area gets you 5 orders of magnitude. And so that's pretty good. It's also possible, since if we could use, say, the 2-meter diameter of the sail instead of the 0.2 meter diameter of the DSOC. So if we could coherently combine on the sail a whole bunch of very, very low power lasers and point them all towards the Earth, we could gain another 2 orders of magnitude. So when you add these together, you can get maybe 7 to 10 orders of magnitude. And so at least in a very, very rough way, you could say, well, yeah, it's within the possibilities of physical laws. It doesn't violate any physical laws. And here's a few examples. You could say, all right, so I've used 3 meters as a sail diameter instead of 2. It's probably more like 2. But you can imagine we're actually building 2 30-meter optical telescopes, at least, that are projects that are currently being discussed. And so this is already 2 orders of magnitude increase in collecting area over Palomar. And so if you do that, so here now I've said, well, if we have 10 hertz of bandwidth and we increase the onboard power, if we could have 1 watt of transmit power on board, then we could get 10 hertz of bandwidth just with 2 30-meter telescopes. If we had, as I said before, a 1 kilometer by 1 kilometer array of optical collectors, and you had 10 milliwatts on board, which was sort of the nominal, and you could use a full 3 meters, you could get 100 hertz of bandwidth. And so this brings up a few other things, which are that technology right now doesn't exist to build a square kilometer optical array for a reasonable cost. And also, because there's so few photons by the time they arrive at this collecting area, you need to be, as people have pointed out, very careful with the filtering and avoiding any background photons. But also you have to avoid dark counts, because dark counts, you have 100 hertz, you have 100 either 100 photons per second, approximately, if you're doing 1 bit per photon, or even fewer. So you need to have 100. Your dark counts have to be less than the photon counts. And remember, you have a kilometer squared array. If these are separated in different telescopes, just to make them more cheaply, because you don't have to have them all, coherently combined, then you have maybe 1 million detectors. So the number of dark counts has to be whatever this number is divided by the number of detectors per second, which is a very low number. And so you can do other calculations. So what if you didn't do it in the optical? Could you do this with a square kilometer array in the radio? And again, the answer is, well, maybe, but you need a watt on board at 30 gigahertz, but maybe you could do it at 300 gigahertz. So anyway, there's all kinds of different calculations that you can do to calculate, what is the best configuration. So we basically decided that we needed to have this R&D effort. All right, and I'm gonna almost at the end, so I feel like I'm doing well. If people have stuck with me, I don't know how many people are still here. So this is how we kicked off a phase 1 R&D to sort of do some really basic, but design study calculations for different things. And so here are the goals for this phase 1 R&D activity. So there are 3 main goals. The first one is to do broad concept studies of link budgets and using different, as a function of different frequencies, using different types of particles even, or any other ideas. And so we were soliciting proposals from people to propose for whatever they wanted to do. The second goal was to, if you said, okay, I'm going to just consider a certain type of system, like an optical comm system or a radio comm system, then do some study where you move forward or design some subsystem components that are capable of meeting the size, weight, and power requirements. These are the very, very strict small, size, low weight, gram scale, and milliwatts or lower power requirements for the onboard system, so the onboard transmitter. And then the third one was to develop and do design studies for the receiving station, so for large area receiving stations or components like narrowband filters for these things. So we had an R&D activity. We had a request for proposal a little over a year ago. And we got a good response, a large number of proposals, and we had feedback, we had webinars, we had Zoom meetings, we also had a workshop to actually write this whole thing, and then we selected 15 proposals. These are the 15 groups that most of them have now started work on their different areas. Here are the topics listed here. And so we are now having and scheduling our first team meeting, which we are hoping to have in person at the end of April here at ASU. And we will bring representatives from all of the teams and talk about progress. I just will make one comment. I've already heard, it's a great group of people, a lot of fun, people thinking of crazy ideas. I've already heard from several of our collaborators that they're writing papers or sending conference proceedings or things like that. One of them, here from Berkeley, who sent me a paper, I think it's going to come out in Nature, revolutionizing laser technology. So look out for that. That'll be really interesting. And I'll just end with some musings or thoughts about things that you might be able to do if you could send science packages or payloads on some of these things. So not even waiting for them to get to the next stars, but and you can go off the bottom of the page, but actually doing science just as they're sailing out of the solar system. So some of the things I would be interested in would be cosmology experiments. So putting a radio spectrometer on board and using the difference in speed, so accelerating to shift spectral features so that you could do a systematic check or a calibration of your measurement. So for a radio edges type measurement, which is something that we know about a lot, or people at ASU have done. I already mentioned the low dark counts. So if you are able to build a receiving station with superconducting detectors that have dark count rates of a very small fraction of a count per second, which is the requirement if you're going to have not have too much background from the dark counts, then you may find, and people have done calculations, that you would actually be limited by many different types of dark matter interacting with these detectors, because the dark matter, you can shield the light, but you can't really shield them from dark matter. And so this large ground receiving station would not only be a very sensitive optical receiver, it would also be a very sensitive dark matter detector, which is interesting. This ground receiver, and people at the University of Arizona are interested in this, because if you put a spectrometer so you can measure the different lines, it would be able to be used for exoplanet imaging, spectroscopy. It's a huge collecting area. You could do lots of exoplanet science with it. You could also do very high angular resolution imaging or sort of an effective optical style event horizon telescope, or resolving the central black hole surroundings in the optical of quasars, which is quasars are these very, very bright optical sources that are galaxies that we're looking down the pipe onto the central black hole in the center of these galaxies. Anyway, there's a whole list down below. You could study the interstellar medium. You could study all kinds of things. on the way. And so I'm going to end with that incomplete list of science ideas. I know I've run pretty long, so if anybody is still left, then I congratulate you. And thank you all for listening. And yeah, so watch this space, and there's I'm sure many questions that you could ask that I would say, well, those are great questions, and hopefully by the end of phase 1 we'll have more answers for some of these.
So thank you, Phil. I think everybody stuck with you the whole time, so that's pretty impressive. Yeah, please put your question in the Q&A if you have a question or comment. There
Oh
we
wait,
go.
I see. Is there? Oh, this is the first question everybody asked. Oh, so I have to say, obviously a great question, because that's the first one. So Tom, the daisy chain question. So Pete Warden likes to use an analogy of Christmas lights for why this is not a good idea. So if you had a relay system, so in other words, if the communication plan was to send the signal from one satellite to the next, to the next, to the next, all the way back to the Earth, the problem is, there's two problems. First of all, it takes at least an hour between launches, and by the time you're an hour, the first one is already out of the solar system. So it's really far away, and communicating between a 2-meter diameter object and another 2-meter diameter object that is separated by the radius of the solar system or distance to Pluto is actually harder, or at least about as hard as communicating from a 2-meter diameter object that's 4 light years away to a square kilometer collector on the Earth. So it's very hard to do. And the other problem is that if you lose one, so if you think about how many of these you would have, right, in between, so you have like 10,000 of them, right? Because the separation, if they're separated by the solar system, if any one of them doesn't work, fails, then the message stops there. The data stops there and it doesn't get back. So the baseline is very much just to go directly all the way from the star system back to the Earth, and then be able to do that and by building a bigger collecting area on the Earth rather than daisy chaining. Now there's a different way. So then the next thing that people do, so I'm sure you're probably thinking along the same lines as all these other people, would be to say, okay, well, what if we could phase them up or somehow have them be close enough so they could communicate and like reinforce their signal? And that's something that 2 or 3 of the groups that are on phase A are thinking about, is how you might do that. So the first answer is just the simple daisy chain. Seems like it's not the best solution. There's actually a paper on that published by Dave Messerschmidt, who's one of the people in the groups already, explaining why that is why that doesn't work in terms of the requirements. A particular idea, the daisy chain, but then there's other people working on other ideas. Sorry, that was a long answer.
All right. Say, Phil, I'll ask you one of the questions on the weight of the payload. I know you had some scenarios in there. I forgot if you had some scenarios that varied the payload weight.
I mean, the weight of the payload, the target it's basically limited by the launch power and the ultimate goal, right? But yeah, there are groups that are studying what if the payload was 10 grams or 100 grams, right? What effect would that have? And at least the basic calculations say that the time to reach the next star increases like the payload weight to the 1/4 power. Okay, so if you go with 1 gram, if you go with 10 grams instead of 1 gram, then it's approximately 1.5 times longer to get there.
Oh,
So, you could maybe start with bigger ones.
Okay. Yeah, it sounds like there's a lot of nice spin-offs happening from some of this research.
Mhm.
Okay, Rick's got a question for you.
Yeah. So how do you make an image when you're flying by the planet or through a star system at 0.2 speed of light? That's I don't know. That's a tough one. You're going pretty fast. I mean, if you can point to the planet from far enough away, right, you can track it, and then you can figure out, okay, well, how long do I have to track it, and how much is it changing in size as a function of time, etc. I haven't gone through those calculations, but they're doable. But I think it's going to be tricky.
Yeah, which team is working on that?
So none of the communications teams are working on that, and that is not one of the three the sort of top priorities. So I think there is a web page actually. So if you go to the Breakthrough Initiatives, Breakthrough Starshot page, these questions that you guys have, you could post them there, and then what in many cases would happen is that the project manager for Starshot, James Skalkvik, would send me an email with your question and say, hey, can you answer this question? And I would maybe try and answer it. But if you wanted to answer it, that would be even better.
That's the breakthroughinitiatives.org.
Yes, I think so. Yeah,
okay.
yeah.
I'll throw that in the chat.
Oh, that was your one.
Yeah, that was the chat link. Oh, okay. There's a new one in the Q&A, Phil.
Okay. I've lost my ability to see the Q&A. Wait a minute. There it is. Oh yes. What happens to it when it encounters a hydrogen atom in interstellar space? So there's a paper on that. Actually, a couple of papers on that question. It's not just hydrogen atoms. So basically, hydrogen atoms are not that bad, but dust particles do cause significant damage. Hydrogen atom just interacting with the hydrogen gas can actually, the main thing that it does is it can heat the spacecraft. So the default plan is to turn it on its side so that the sail is not, you're not sailing into the wind, basically. And then you have a much smaller cross section to the hydrogen gas that you're going through. But the front edge will still get impacts. And so the estimates in papers that have been published on this are that the actual temperature of the chip and the spacecraft would be not that cold. So not like 10 Kelvin, 20 Kelvin interstellar space, but more like 100 Kelvin. And this is a problem because just due to hydrogen gas impacts, this is a problem if you wanted to use, say, superconducting electronics to save power. But there's also been studies on dust, in interstellar dust. And one of the big questions is we don't actually really know very well what the interstellar dust and the interstellar content is between us and Proxima Centauri. But so dust particles can blow holes in the sail. They can do all kinds of stuff. So yeah, that's a good question. On the flip side, if you calculate, it's approximately, I think, something like 5 milliwatts of power, of energy, kinetic energy, in just hydrogen atom impacts, on the edge, on the forward edge of the sail, as you're going through interstellar space. So people have talked about possibly using that as a power source, because it'll be a thermal, it'll generate a thermal you could have a thermal power source, and if you're radiating elsewhere on the sail, if you're radiating and shielded from the hydrogen and radiating to space, you can have a temperature difference and drive current that way. Anyway, the papers by Avi Loeb and Bruce Drain, who's a professor. So Avi is a professor at Harvard. He also is really interested in Oumuamua and other, crazy alien things. And Bruce Drain is a professor at Princeton who studies interstellar dust and did a lot of the theory for dust that underlied another experiment of mine called BLAST, looking at dust polarization. So that was a long answer. And then the other one is the payload assumed to be separate from the sail. Could the sail incorporate some of the payload? Yes. So the idea is definitely to integrate, say, the laser, the transmitter throughout the sail in order to make use of the large area. And so a bunch of teams are studying different ways. So there are actually people who are studying the sail material and are working on the communications part on the side of the transmitter on board.
Yeah, two months ago we had Steve Desch give a talk pretty much on the Avi Loeb rebuttal.
Yes.
But we haven't given Avi Loeb his fair share.
Well, I could ask him. I'm sure he would be happy to come and talk to you. I mean, after all, he was happy to go and talk on Fox News with Tucker Carlson. He was happy to talk with Joe Rogan and lots of other people. So I'm sure he'd be happy to come and talk to all of you.
We have, so another question. Nice.
Yes. So actually there is a fourth working group that's got no money yet, but working on the question of power, which is why I mentioned the hydrogen power from the hydrogen gas just passing through. And one of the ideas for power is to generate power from photovoltaics or on board using the light from the star. Of course, there's a couple of problems. First of all, you're going past the star again really fast, so you're not very close to it for very long. Second of all, if we're going to Proxima Centauri instead of Alpha Centauri, it's not very bright. It's an M dwarf. It's a lot fainter intrinsically than the sun, so you got to get a lot closer to even get the solar power density. It actually turns out, this is another calculation we did, if you use the beamer and you send us the signal and you hit the probe with the beamer when it's all the way at the star or when it's nearly there, over the area of the sail, it actually, you can calculate, it's like for 100 gigawatts on the Earth, it's 10 milliwatts of power, which isn't nothing. So you could even like uplink power, right? If you have photovoltaics on board from the beamer. Of course, it's not very efficient. You're using 100 gigawatts to get 10 milliwatts. Anyway, so the problem is that you can integrate the amount of starlight that you get and star power, and it's not that much. So the solar cells are definitely one thing that people are looking at for a power source. All right, next one, because I saw this comment earlier, magneto tails can be used to launch solar sails. And then you're using particle beams. I mean, I think there are, I don't know very much about that one. But what I do know is that there are lots of different ideas for propulsion that people have been looking at. I guess I would say the propulsion idea that I think is to me personally pretty interesting is that there's a company I think called Helicity Space, I think that's what it's called, that is working on and claims that they have a way of doing a fusion propulsion system. This is a pulsed fusion, so it doesn't have to be contained like a fusion, generator plant. It's just pulse because you're using it for propulsion. And if you can do fusion propulsion, then you need a lot more weight, but you can also accelerate more massive things. So, but magnetotails, I'm sure there's other things like that as well that people are looking at. So the whole propulsion business is like there's a lot of stuff going on. Okay. Yeah. So I know there's a lot of interesting work going on propulsion, EM drives. I mean, yeah, and actually I will say, so on the propulsion side, so one of the workshops Tom and I went to was this Interstellar Research Group meeting in Tucson, where a lot of the talks and a lot of the work was on different propulsion ideas. So Breakthrough, every year, the Breakthrough Initiatives has a meeting, a general meeting called Breakthrough Discuss. This year it's going to be in June in Santa Cruz, and one of the days they decided that they're going to invite the Interstellar Research Group, IRG, to participate and have one day in Santa Cruz where they're talking about IRG type topics. So if you go and look up Interstellar Research, if you have ideas for propulsion and things like that, if you're not already connected with the Interstellar Research Group, I think that's definitely a possibility for you to look into. All right, it's 9 o'clock. And I am amazed that we have so many people still. So yeah, I will say thank you and be well and safe, and then I'll hand it back to Tom and Claude.
Thank you, Phil. Yeah, that was pretty interesting. I can't let this one go, Phil. Walt Novinger has one on quantum entanglement for communications.
Yes, absolutely. So that is also something that has been that has been proposed, and I think the current thought is that quantum entanglement, at least according to sort of the normal ideas about quantum entanglement, is that you can't actually use it to transmit information, at least not faster than light. You can use quantum entanglement and quantum effects to increase the amount of information that you are sending, or the signal to noise, or whatever, the bits per second that you're able to send for a given, say, weight and power. And so that's being actively studied by a number of different teams in this phase 1 R&D. Although, unfortunately, I would say it does turn out that usually by using sort of the most advanced quantum techniques, usually what you find out is that you gain sort of a factor of 2 or something like that, not like a factor of infinity or 1,000 or yet. So we haven't quite figured out how to use quantum entanglement to gain more really than a factor of a few. But that's definitely something that people are working on, and we're supportive of and interested in. So yeah.
Yeah, I'm sure 50 years ago, the technology we have now in New Horizons would have seemed like unattainable, or how do you do that? And so I think we're looking into the future and how to gain a few more orders of magnitude and things we don't know how to do right now. So a lot of good ideas should come out. Thank you, Phil.
Thank you, Phil. We really appreciate it. We're going to run this by Scotty to see how it maps up to the Star Trek canon. But it really is a cutting edge discussion, and really kind of very mind-opening to see the type of thought that goes into these NASA probes to find kind of the best solution among all of those others, all of the options. So we appreciate it. I think that's it. If we don't have any more questions, our next meeting is going to be via Zoom on April the 15th. Again, thank you for being here tonight. I think we're still at 47. So we lost a few in the last few minutes, but we had a high of 65, and I think that's really great attendance, and we appreciate your participation with us. Don't forget the Messier Marathon, and to check in with SAC for that. And we'll be posting some things on Facebook as we get more information too. So with that, having a lovely evening. And now you can go back and watch the rest of the basketball games.
All right. Bye, everybody.